The Central Valley Salinity Coalition is a stakeholder-driven program dealing with looking at sustainable salt and nitrate management planning for the entire Central Valley of California. So objectives of this particular program, we're focusing on a management zone. So this is a construct that the CV Salts Policy Group and Executive Committee have come up with to look at the management of salt and nitrates by one or more entities in an area, and particularly for salt and nitrate management plans, and this is related to the State Water Resources Control Board's recycled water policy in California. This particular work focuses on looking at management strategies and a technical look at them using tools and methods and approaches, not necessarily something that would be needed for every area, but in more complicated areas, some of these tools would be more helpful. So the study area is south of here in the southern part of the Central Valley. It's surrounded, or it's within several groundwater subbasins. The area that we are working with was actually pre-selected, and it's shown in the blue outline here as Alta Irrigation District. So we were just tasked, with a specific area, and the first thing that we needed to do then in order to use the tools was to expand our study area appropriate for the use of a groundwater flow and transport model. The things that we were focusing on were salt and nitrate strategies, and we worked with the stakeholder group in order to arrive at what those would be. We were trying to limit the number of variables that we were dealing with, but the ones that we focused on were a decrease in the use of irrigation water, so an increase in irrigation efficiency, more drip irrigation, also local recharge. That was part of scenarios 1 and then part of scenario 3. Scenario 2 was focused on a decrease in the nitrogen loading. So basically, scenario 3 was the best of both worlds of scenarios 1 and 2, and that's the one I'll show some highlights of results for in a few moments. The other one that I'm going to touch on came about later after we showed initial results. We were actually asked to do an extreme scenario. So not a real scenario, but there was an interest in looking at a bookend. So basically the extreme scenario was a no agriculture whatsoever scenario. The tools that we were using involved the soil water assessment test modeling application. This was work done by another one of our team members, and it involved looking at all of the processes in the root zone. Their work resulted in the flows and the concentrations for salt and nitrate coming out of the root zone and then utilizing that information within the groundwater modeling effort. So what this did is it basically circumvents, the deeper vadose zone. It's a conservative approach, takes that information direct from the root zone and into the groundwater flow model. So there are some things to think about in other applications where there might be other modeling approaches utilized on top of these. The numerical model was based on the US Geological Survey Central Valley Hydrologic Model. As a starting point, we used the aquifer properties from CVHM. We refined the grid from a 1 mile grid to a 1/4 mile by 1/4 mile. The layering went from CVHM's 10 model layers to 38 layers. We were looking to track the salt and nitrate on a very fine scale across this study area. We also used the flow model as a steady state model with MODFLOW 2000, and then applied the transport model with MT3D MS. And then there were other MODFLOW packages utilized as well. The important thing about the groundwater volume changes that I wanted to illustrate here, there are slight reductions in the fluxes due to the pumping reduction, the lesser amount of irrigation water applied. These are shown in the bar charts on the top left-hand corner of the slide. On the right-hand corner, we have the reduction in the recharge because of the lesser amount of irrigation water applied. The lower two images show what's going on with just looking at the number of dots. These are recharge sites in our baseline conditions, so these are artificial recharge sites. And the important thing here is in our baseline and scenario 2, we have a lesser number of sites, and then when we move to scenarios 1 and 3, where we increase the irrigation efficiency and we increase the recharge, artificial recharge is only increasing external to our so-called management zone. In this whole project, it came about that the other entities external to the management zone proper were sensitive to model results being shown. So it's difficult to explain results for the areas where we actually had more recharge going on that was part of the modeling effort. This is another slide that sort of emphasizes that point, where this is looking at just the recharge volumes in total, and we can see here that when we're just looking at the AID portion of the model area, that we have no additional recharge due to artificial recharge, that it stays the same as our baseline condition. So on the nitrate mass and TDS mass changes, we have increasing reductions in the nitrate mass from scenarios 1 and 2 and 3. Part of this is due to the reduction in the irrigation water. We're accounting for the mass in the irrigation water itself and the decrease in the nitrogen loading in scenario 2. And in the TDS mass, here it's mainly because of the reduction in the irrigation water that we also have a reduction in the salts. To explain a few terms before I get to the results, this is a schematic of the aquifer system, and the terminology that we're referring to by zones. We're referring to an upper zone, and this is basically taking an organization of the detail from layers 1 through 22, and then combining that information to describe the upper part of the aquifer system to a depth of about 300 feet. And then the lower zone refers to all of the synthesized results for the additional layers to layer 38. This made it easier, otherwise we had volumes and volumes of results for each layer. So I'm going to hit on some key results for scenario 3, which was sort of the best of both worlds. Our scenarios 1 and 2, where we're reducing the nitrogen loading and we have an increased irrigation efficiency. Skipping. So this is the upper zone. In the upper right-hand corner, we have an illustration of what occurred from our kriging of actual observed results of our data. And then in the lower 3 images, we have what happened with our model simulations from 5 years to 100 years. And we're showing here we have an actual decline. So even though we have the best of both worlds and we reduce the nitrogen loading according to what the stakeholder group determined, and this was different nitrogen reductions for each commodity in the area. So we have the largest change occurring between years 5 and 50, and then we have a decreasing change from years 50 to 100 years. We're basically moving towards an equilibrium, but it's still declining. And these concentrations are above the MCL at the orange colors and above. In the lower zone, we had some improvement. So from 5 years to 100 years, we see a decrease in the intensity of the colors. But again, the orange color means it's still above the MCL of 10. So there's a large area that even after 100 years in the lower zone, that this scenario 3, the best of both worlds, is not moving towards an achievement of water quality objectives. TDS in the upper zone, we see a similar sort of thing. We see the most rapid change in the simulation between 5 and 50 years. But again, we see a decline in the water quality, and then we see some further decline when it goes from 50 years to 100 years. And lower zone here, sort of similar to nitrate, but we have more salt in the system. We see some decline. Gosh, this is on the west side of our management zone area. but some improvement in the very southeast of the model area. So we're going to look at a few results for the extreme no ag scenario. Here we went to this what I referred to as the no ag whatsoever. So that meant we were doing no agricultural irrigation. We changed our entire model information for all the pumping that we had going. It kept the municipal and other non-ag pumping. We removed nitrogen loading solely due to agriculture. So this was, as I mentioned, the point of it was to have a bookend. We were looking at what the effect was, and this was something that was requested by both environmental justice interests and also ag interests to know, well, what exactly would we accomplish if we took away this loading altogether? And the important thing to remember here is that there is a pre-existing legacy condition in the groundwater already. So this is an area, as I showed earlier, in the actual observed water quality, it already has very high nitrate in groundwater quality. So this slide shows what happens when we look at the comparison in water fluxes between the baseline condition and the extreme no ag condition. And we see in the relative magnitude of the decrease in pumping and the change in the pumping. We have a lot less pumping and we have a lot less recharge because we've removed ag. And we have a flow into the system from the east going in the direction of the west, but most of the outflow is to the south. So what this is doing is largely not removing as much from the system, and we have an effect of the flow that's coming into and out of the system. And so this affects what happens to the mass that was the pre-existing legacy condition already in the system in groundwater. So here in the nitrate upper zone, we see that there's an improvement between the 5-year and the 50-year. And we see also that the largest improvement is in the southeast part of the model area. This is where we had that large inflow into the system, but we also have very little flow out of the system going in the westerly direction. Most of it's to the south. So we see an accumulation of that mass on the west side of our management zone area. So even though there's an improvement, there's an area that still is below or not achieving water quality objectives, even when we've done all of this. Similarly, for the upper zone TDS, we see an improvement on the southeast side of the model area, and for the same reasons of flow and how the mass is staying essentially trapped in the system because of the flow dynamics. So we can see from this slide just an overall depiction of how mass has changed from an early time to over the early portion increasing and then moving towards an equilibrium condition. And this is, both of these are for nitrate, the upper zone and the top slide. There's a little bit of change in the no ag scenario, but it's a very slow change. In the lower zone, this is where we see the most effect. So the main thing that we saw in this is that this is a regional system. This is a non-point source, which is a very different animal to try and deal with. So some of the approaches, the engineering approaches that are more often looking at point source remediation, that they're likely not to be very practical on the non-point source scale. The nitrate and the salt move very slowly in the system and they're affected by other flow drivers. So the concept of looking at restoration to water quality objectives or even so far as background water quality conditions is likely not very practical or feasible in many cases. So it will be very important in the future to look at what are the priorities in the area, what are the things that might best be done to achieve the first and priority goal for CV salts is having potable drinking water for communities, particularly the disadvantaged communities. The second goal is achieving a balance between salt and nitrate utilized in an area, land use and water management, in order to limit continued degradation. But the third goal, the restoration goal, that's the one that's going to deserve a lot of attention to whether or not it's feasible and whether, resources invested, that there's priorities, and to look at, what has the most benefit and the most protection and the most care for improving groundwater quality. Thank you.
Do you have a sense of how much of the delay of the transport is in the unsaturated zone and how much is in the saturated zone?
So that wasn't part of what we were modeling. So it's hard to say. And I'd say even the data that we were receiving from the SWOT modeling effort for the root zone, and then taking that information directly into the groundwater flow and transport models, that it would be useful in the future to have field tests to further verify what that information is, because there were some higher numbers and there were a lot of changes. Each commodity and the reduction in loading was specific to each commodity. And I think that there's more room for looking at how do we handle the vadose piece of it and all the mechanics in the vadose.
Thank you for the talk. I have a question about the refinement, vertical refinement of your model from 10 to 38 layers. I know, or I assume it's needed for the transport modeling, but I was wondering if you had enough borehole data to support such a refinement in the vertical direction, or what kind of data become available to support it.
We are mostly looking to just discretize it vertically, so it wasn't based on additional information to a large degree other than from what we were able to look at within CVHM. So we have all the lithologic model data for CVHM and the borehole data from that. So there is a fair distribution of control in the area. So we were using the existing information.
You may have answered this already. In terms of irrigation efficiency, were you making assumptions based on crop type or the system type?
We were assuming that the efficiency meant that it went to 80% drip. So it was a change from more current practice, maybe several years ago, prior to Irrigated Lands Regulatory Program, to moving to 80% drip.
This is a little off-the-wall question, but if in your model, when you've got active agriculture, you're bringing up a lot of water and then you're infiltrating a lot of water, if there was a step in there, such as treatment wetlands or things like that, that were removing the nitrate, did you look at a scenario like that? Would that accelerate nitrate cleanup in the subbasin and have an effect?
It's a good idea. So no, we didn't look at that kind of a scenario. However, there's discussion of a restoration scenario, and I think that the parameters for that will be derived from work done by CDM Smith on a nitrogen implementation measures study and a salt measure study, where they both were looking at restoration for nitrogen in one report and salt in another report. And so there would be added measures to try and more actively address the constituents.